The last video I put up looked at the idea of forces on objects that were on or moving across a horizontal surface. But what happens if something changes, such as my object is now on an incline? Well, things that would vary. One, our normal force. In the last problem, one thing we could assume, or last video, one thing we could assume was that the weight of the object, which always points straight down, regardless of where the object happens to be, would line up directly. Let's put a little horizontal guy here, with the normal force. He might not be equal and opposite in value, but they did both act in the same plane. Well, the problem, or I should say the situation with an incline, is normal forces always act perpendicular to the surface. So to be perpendicular to an incline, my normal force and my force of gravity no longer will point opposite each other. They're going to be pointing differently from each other. The other thing that is going to be different about these problems is that when a horizontal surface, your force of gravity has no no x component. It doesn't in any way contribute to the motion of the object across that surface. But on an incline it does. On an incline, some of the weight of the object is going to serve to try and move the object along the incline. So there's two slightly different things about these particular types of problems, and we'll work through them slowly as we move through this video. So let's take a nice box. Whoa, that's going to be a very steep incline. Wouldn't want to pull the box up that. A box on an incline. His mass will be 45 kilograms. We'll start there. And as we did in the last video, we'll take it stepwise, solving for things as we go. The first thing we might want to know or be asked is, what is the normal force? What's the normal force acting on this box? Well, I would be given the mass of the object, and I would also be given the angle of the incline. Let's say it's 20 degrees. In order to find the normal force, is it going to be related to the object's weight? Yes, it will, but in a slightly interesting way. Since I don't have the two lined up perfectly with each other, how am I going to go from this to this? Well, if I do a little geometry, I find that the weight of that object is actually the hypotenuse of a right triangle. One side of that right triangle is perpendicular to the incline, and therefore lines up with the normal force. Therefore, that side of my triangle is going to be, in this case, since there are no other forces acting in the y direction, equal and opposite to the normal force. Now, how do I get that side of the triangle? Well, again, because geometry is magic, this angle right there is actually the same as the angle of the incline, 20 degrees. Since this side of the triangle is the adjacent side of the triangle to that particular angle, I'm going to use the cosine function. So my normal force, in this case, will be equal to the weight of the object, which we said the mass was 45 kilograms. 45 kilograms times acceleration due to gravity, i.e., the weight, times the cosine of my 20 degrees. And when I solve for that, I wind up getting 414 newtons. Now the weight of the object on his own is 441. So in this case, my normal force is going to be less than the weight of the object. So when I take an object and he's on a flat horizontal surface versus putting him on an incline, as I put him on an incline, the normal force is going to decrease. And the steeper the angle, the lower the normal force will be in relation to the actual weight of the object. So if you're given an object just sitting on an incline and you're asked to solve for normal force, weight of the object is the hypotenuse of a right triangle where one of the sides is going to be equal and opposite to the normal force. That side of the triangle we find using the cosine function. So the value of my hypotenuse, the weight of the object, times cosine of the angle will give me my normal force. Now, what happens if he is being pulled along the incline? So the last set of problems, we started with an object stationary on a horizontal surface, and then we added a pulling force. So let's do the same thing here. I'm going to have the same mass, which would mean the same weight, 441 newtons. I'm not changing anything about the fact that he's on a 20-degree incline, but I am going to give him a big fat pulling force of 300 newtons, and I'm going to make the angle 15 degrees to the incline. So I'm dragging the box up the hill. I have a little strap. The little strap makes an angle with respect to the incline. What's my normal force? Well, conceptually, it's exactly the way we worked it last time. On a horizontal surface, if I have a pull that has an upward component, that upward component will subtract from the downward portion, in this case, of the weight of my object. Now, we said the downward pull here was 414 newtons. So my normal force would be 414 newtons minus the upward component of my pulling force. Since that side of the triangle is opposite of my 15-degree angle, I'll use the sine function. 300 newtons, sine of 15 degrees. And I wind up getting a normal force equal to 336 newtons. So the steps conceptually for taking an object on a horizontal surface, giving him a pull, and having the normal force be the weight of the object minus the vertical component of the upward pull, is absolutely no different than if I put him on an incline. The one difference is how I go about finding that normal force. I don't look at the full weight of the object. I only look at the component that is lined perpendicular to the surface. Now, in the previous video problem, our next step was to go to friction. And so let's go ahead and do that here. I have the same setup. That's not changed. My weight, 441 newtons. I'm going to give him a pull, the same one, 300 newtons. Oops, looks a little sloppy. At 15 degrees. I solved in the last bit for the normal force of 336. But let's say in this case, when my list of information was given in the problem, along with the mass, I was given a coefficient of friction of 0.19. And this problem asks me directly, solve for the force of friction acting on the box. Well, my formula, coefficient of friction, is force of friction divided by normal force. That does not change even if he's on an incline. I know my coefficient of friction, 0.19. I know my normal force is 336. My force of friction comes out to be 63.8 newtons. Down the incline. I'm pulling him upwards. Friction always acts opposite the direction of motion. Exactly as we did in the last problem. And if I wanted to go then the step further, as we did in the last series of problems, and ask for acceleration, here is where I run into an additional twist. Object on the incline. I've got forces acting on him. And there's actually one guy I've kind of forgotten about at this point. I've got the applied force. I've been working with him. I use the normal force in solving for friction, and I use the weight of the object to help solve for the normal force. But when I looked at using the weight to solve for the normal force, I broke that weight into x and y components. And I used one component to actually work to get to the normal force. But I can't forget he does have a second component. That second component is directed down the incline. So when I am looking at forces acting on my box, I do have a force that is starting to pull him up the incline, the x component of the applied force. But I can't forget I do have a piece of the weight that's also acting in what would be the x direction or along the incline. Now that particular force, since it is opposite the known angle, I would find using the sine function. Down the incline also, though, is the force of friction. So in this case, for this problem, if I go to solve for acceleration using Newton's second law of motion, I have three forces that make up my net force. I have the applied force in the x direction. I have the force of gravity, or the weight of the object, that's oriented along the incline. And I have the force of friction. So, we just in the previous example solved for the force of friction. Now we have to get to these two. The force applied in the x direction, since this is the adjacent side of my known angle, which was 15 degrees, I have 300 newtons, cosine of 15 degrees, and that wound up actually being 290 newtons. Oops, getting my 9. The force of gravity that acts down the incline is this side of the triangle, and since it's opposite the known angle, I'll use the sine function. We already said the weight of the object was 441 newtons. So 441 sine of the incline angle of 20 degrees. And we wind up getting 151 newtons. So my net force would be a positive 290 newtons, since that's up the incline, plus a negative 151 newton, since that's the force of gravity down the incline, plus my force of friction, which was 63.8 newtons, and it will be negative because it's also down the incline. My net force winds up being 75.2 newtons. Since that is equal to mass times acceleration, if I divide that value by the mass of 45 kilograms, I get an acceleration of 1.67 or 1.7 meter per second squared, positive, up the incline. So just as in the problem on a horizontal surface, if I'm asked directly for acceleration, I will be given mass of the object. I would be given, well, where am I going to write them? I'll write them right there. The coefficient of friction, because I'm going to need that to unlock the frictional force. And with that information, I could work to get acceleration. First thing I would do, find the net force. Second thing I would do, using net force and coefficient of friction, find the value of my frictional force. Find the value of the applied force in the x direction and the weight of the object also acting in the x direction or along the incline. Using the force of friction and these two, solve for net force, and then lastly, solving for acceleration. Now sometimes you do get lucky, sometimes you get lucky. You're given a box, he's on an incline, and we're told at that point he is at equilibrium. Oh, that's a terrible looking equilibrium, but you can read it. In that case, knowing I have a towing force, and knowing I do have a force of gravity acting in down the incline, that direction. In that case, solving for something like friction becomes easy. So sometimes, if in a piece of information, in a problem, you're not given coefficient of friction directly, look to see if you have information that you could get friction with besides using that. In other words, if we're given a pulling force, we could also just work this problem knowing that I have a force in the x direction this way, one force in the x direction that way, and if I am in equilibrium, my force of friction right there, these two forces would have to sum to equal that guy. Otherwise, I would not have a net force of 0 along the incline. So if I'm not given my coefficient of friction, look to see if they say the box is moving with a constant velocity up the incline, or it's at rest on the incline, perhaps being held in place by a rope. If that's the case, all I need is my force applied in the x direction. From that, subtract the force of gravity in the x direction, and that would equal the force of friction, because the sum of these two would have to equal this guy for the net force to equal 0. But you do have to look for those key words. It's in equilibrium. It's being held at rest. It's moving with constant velocity. All of the things to say net force is 0, then we could go and use this type of a relationship. Aside from that, look to be given your coefficient of friction. With the normal force, you could solve for the force of friction. These two forces you can piece out using the applied force and the weight of the object to then get net force and acceleration if it was necessary. Alrighty, hopefully that'll help a little bit with these problems. If not, you're always welcome to stop in and get some extra help.